Hey guys, today we're going to be talking about circuits in the frequency domain. So let's get straight into it. So we have resistance, right? And this is in the time domain, right? So we have V equals IR. But then if we go into the frequency domain, we have our using Laplace transform or some other transform to go into the frequency domain. We get impedance. And this would be in the frequency domain. And instead of V equals IR, we have big V equals big Z, or V equals IZ. And you'll notice I'm using capital letters. Typically we'll use capital letters to signify that the function is in the frequency domain. So yeah, the Laplace transform converts time domain to frequency domain. So we're going to be using the Laplace transform to turn our components into the frequency domain, right? So, as I said before, typically the notation of, let's say we take the Laplace transform of f of t, we'll get out f of s. And so what s is the complex frequency. So we have two components and then the frequency component. So we'll have this part is exponential decay, and this part is sinusoidal. We're only going to look at this part in more advanced classes. You'll see the exponential decay as the transient term, but we're only going to look at sinusoidal steady state, which is after a long time. How does the circuit react? So we'll see, we won't see e to the st, but we will see cosine wt. We won't see this, we will see this. Alright, so let's get some basics of Laplace transform in the way. So if we take the Laplace transform of the derivative of a function with respect to time, we will get out the Laplace transform of the function. Let me rewrite this bigger. Or we just multiply s to the function itself in the frequency domain. If we have the integral in the time domain, we'll get out just dividing by s in the frequency domain. And so this brings us to our components. Let's first talk about our resistor. Okay? V, and this equation for this is V equals IR. Take the Laplace transform of both sides, we get V equals IR. R is just a constant. And so if we find V over I, aka the impedance, we get R. So we see that the resistance and impedance doesn't change for a resistor. Let's talk about the inductor. So the equation for this was V equals L di dt. If we Laplace transform both sides, we get V equals SLI. Find the impedance by finding V over I, we get SL. And since we're ignoring the complex exponential, S will just equal omega W. So this just equals J omega L. Next, let's talk about the capacitor. The equation for this is I equals C dV dt. Laplace transform both sides. We get our I equals SCV. If we find V over I with random things, we get that the impedance is 1 over SC. And if we ignore the exponential decay component, we get 1 over J omega C, which is also equal to negative J omega C. So you notice the resistor has real impedance. The inductor has complex positive impedance. And the capacitor has complex negative impedance. Okay? And so we can replace, knowing this, we can replace inductors and capacitors with resistors with complex impedance. Okay, let me show you what I mean. So let's say in the time domain, or what we've typically worked with, we have a circuit. Let's say we have a voltage source and it's connected to a resistor, and then we have here goes to a capacitor. Here we have another resistor, then we have an inductor here. Let's say this is 100 ohms, this is 200 ohms, this is a microfarad, and this is 1 millihenry. So when we move to the frequency domain, we have, or let's say V equals 5 cosine 100 t plus 90 degrees. This is V. Alright, when we move to the frequency domain and redraw the circuit here, here we have, here we go. Instead of a capacitor, we'll have a complex resistor. And the resistors will stay the same. And instead of an inductor, we'll also have a complex resistor. Okay, and so let's look at our formulas. The impedance, or V over I in the frequency domain, is just R. for a resistor. The impedance of an inductor is j omega L. And the impedance of a capacitor is negative j over omega c, right? And so, actually, let's make this 1,000 radians. So we have a frequency of 1,000 radians per second, right? And so we can just plug that in. So with a frequency of 1,000 radians per second, Z, or our capacitor impedance, equals J times 1,000 times L, which is 1 millihenry. And so we get an impedance of 1. Do the same for capacitor. We have J, negative J over 1,000 times 1 microfarad. We get that this has a impedance of negative 100J. And so we can just plug those in. So negative 100J, 1J, and then here we have just the same, and this will stay the same. And our voltage will just be the phasor. So we have 590, because we have here 5 and 90. Okay, so let's do an example. So we're gonna have a voltage source and a resistor, an inductor, and a capacitor. So this will have value of 100 ohms, so the value of 50 microhenries, and this will have value of 25 nanofarads. I have V here, and V equals 7 cosine 1,000 t minus 45 degrees. So what we're going to do here is we need to convert this circuit into a steady state frequency domain. Equivalent. Okay, and so what does steady state mean? Basically, it just means to ignore the exponential decay part that we saw over here. So we'll just be working with j omega as S. So let's remember our impedance formulas. We have R, it's just going to be the same. For the inductor, we have j omega L, and for the capacitor, we have negative j over omega c. So if we look at our voltage equation, we see that we have a frequency of 1,000. Okay, so W equals 1,000. And let's go ahead and plug that in. So for inductor, we have J times 1,000 times 50 microhenries, and that equals J 0.05. You plug that into our calculator. And then for our capacitor, we have negative J over omega, or 1,000 times 25 nanofarads, Put it into our calculator, we get negative 40,000 J. Okay, so let's just redraw our circuit. The voltage source. So first we have the resistor, and that stays the same. But for this inductor, I'm going to draw red here, we have a complex impedance which was calculated to be 0.05. And then for the capacitor, another complex impedance. We're going to have that be negative, or let me put the J in front, negative J 40,000. And then finally our voltage source, we're going to write the phasor for it. We have the amplitude as 7 and our phase as negative 45. So we have 7, negative 45. And this is our answer.